Hi. For the next section, we'd like to discuss about the stratification and regression estimation. So similar to chapter 3 under the simple random sampling, that when we doubt about the linear relationship between x and y variable, using ratio estimation could be a bias estimator if a least square line of the variable x and y does not pass through the origins. That means if the y-intercept does not equal to 0, that could be a problem. So that's why we like to progress into the regression estimation, that with the variable x and y, we try to plot a least square regression line, and then we can estimate the y bar for each of the stratum using a linear regression estimator. Okay, similar to the ratio estimation, we would have a separate method and a combined method for the stratified random sampling. Let's look at my lecture notes, my written notes. So very quickly, we can revise on the simple random sampling under the ratio regression estimation, that we need to look at the variable x and y from the sample. So we make use of the sample y bar, subtract the beta, which is the slope of my regression line, multiplied to the difference between the sample x bar to the population x bar, and we use this relationship to estimate the y bar for the population under the linear regressions. The beta is defined as the optimal beta, that is equals to sxy divided by sx squared. And we also discuss about how we estimate the variance of y bar under the linear regressions method. That would equals to the final population correction factor multiplied to s squared over n. In this case, s squared is equals to sy squared minus 2 beta sxy plus beta squared sx squared. Or alternatively, we can say that the estimated variance under the linear regressions is indeed equals to the variance of the y bar under the ordinary estimation multiplied to 1 minus rho square. Rho is the correlation between variable x and y. Okay. Stratification, that means we have a population, then we divide the population into different strata. We obtain each of the stratum y bar, or the sample average of y, add up all of the y bar by the weightings of their populations. And the estimated variance will equals to all of the estimated variance of each of the stratum, adding up weighted by the population square. So that would be the stratification method. If we combine stratification and regressions, that we would have firstly the separate method. The separate method of the y bar under linear regression separate methods is equals to, again, of the y bar of the stratum, adding up weighted by the population weighting. But in this case, we estimate the stratum y bar using a linear regressions method. Okay, so presumably within each of the stratum, we would have a linear regressions of x and y, linear regression of x and y, and each of the slope or each of the beta could be different. And then the estimated variance will equals to, again, the estimated variance of each of the stratum y bar, adding up weighted by the population's weighting. And that could be defined as this formula. Okay, alternatively, we could be using the combined method. Combined methods, that means we first, using stratification, that we add up all of the sample y bar of each stratum, weighted by the population. We also add up all of the x bar from each of the stratum, weighted by the population weighting to first find the y bar and x bar estimate. Using these two variables or these two values, we have a combined method of the linear regression estimation. So y bar obtained from these equations minus beta multiplied to the x bar under our sample stratifications, subtract to the true population x bar, assuming the true population x bar is given. The question is, what is beta for the combined method? So if you refer to the lecture notes, for simplicity for the calculations, beta in this case will be a weighted average of all the strata slopes. So that means we need to calculate each of the beta for each of the stratum, and then we find the weighted average of that. So in other words, we are trying to add up all of the beta weighted by Qi. And Qi is defined as the finite population correction factor multiplied to Sx squared divided by n and multiplied to the population weightings. Okay, so the estimated variance of y bar under the combined methods, again, that would equals to the finite population correction factor multiplied to S squared over the sample size and weighted by the population's factor. Or alternatively, we would have a more simplified version of the estimated variance of y bar under the combined method. And as it was said in the lecture notes, that the minimum value of the variance of y bar under the combined method is defined as the variance of the linear of the y bar under the separate method plus a factor. Okay, so this is the case. This factor is defined as Qj, which is the same as what we defined up here for the weightings of each of the beta. Okay, so it is equals to the finite population correction factor multiplied Sx squared divided by the sample size weighted by the population factor. And this Qj would be used as a weighting to multiply to each of the beta for each of the stratum, difference to the overall beta, and taking a square. So this is a non-zero or greater equals to zero value. This is a non-negative value. So if we look at this relationship, we can confirm that the estimated variance of y bar using a combined methods is always slightly greater than the variance of the y bar using a separate method, as long as this value does not equal to 0. For the separate methods, we always require more information because we need to have a separate true value of x bar. For the combined method, we need the information on the overall x bar. And for the separate methods, we need to assume that each of the stratum's size is large enough, as well as the sample size of each of the stratum must be large enough. And each of the beta, they could be quite different. Whereas under the combined methods, if we assume the beta is quite similar to each other, then we can apply the combined method.